so I'll keep going. So where we left off was we proved what? We proved that Rademacher complexity gives you the generalization bound. You have the gap, you want to bound it. There's the sampling error, which is the log 1 over square root of m term. And we added the Rademacher complexity. But what we didn't do was give an example of anything, any calculation of the Rademacher complexity. So that's what I'm going to do now. Okay, so we're going to set up SVM, which is called support vector machine, but it's just linear, and estimate the Rademacher complexity. Okay, so we're assuming that our data set S is always contained in this ball. And our hypothesis space is just these linear functions that are bounded by a certain constant. Now in practice, you don't train on this constrained problem. You train on the relaxed version of it, where you minimize the loss plus, some lambda times this norm, or this norm squared, which is just as good. Okay, so the theorem is okay. So the theorem is the Rademacher complexity is bounded by, you've got the 1 over square root of m term, which we're happy with because we have that term anyways. And then the constants in front are just the bound on your data and the bound on the weights. Okay, so let's prove that. Okay, so the definition So that's the definition of the Rademacher complexity applied to this hypothesis space. Because the general definition is it's the expectation over sigma, our plus 1, minus 1 variables, multiplied by the functions over all functions in the class. Well, the W bound is covering the functions in the class. The functions are just W dot x, and there's the sigmas. Okay, so what we're going to do, the first step of this is to rewrite it as, since it's linear, sigma is times xi. Okay, and then what are we going to do after that? What do we do with dot products? Is Cauchy-Schwarz. Okay, so let's pull that all the way out, and the norm of W is bounded by lambda. So right away we get a little more space. What's left? Just the norm of this whole vector. And now for this vector, I'm just going to use Jensen's inequality. It's norm, expectation of some vector, is the square root of the expectation squared And then let's just see what, and then, sorry, is less than or equal to expectation squared square root, yeah. Yeah, that's Jensen. So what's that? So it's the expected value over sigma. Now I square it. So it's sigma I, sigma j, xi dot xj. Now we haven't taken expectations yet, but now we can use the independence of the sigmas. So all the cross products cancel out. So now we've just got sigma squared, which is 1. Now, did I lose the square root? Yeah. Great. So what's that? That's bounded by each xi, this is norm, each of these is less than or equal to r. So we've got m r squared to the 1/2. And so that's where we get lambda over m square root of m r squared. Which is the bound. Okay, so that's great. So we bounded it in a pretty simple way using linearity. Is that good?
So
Yeah.
if we just directly bounded sigma xi by Cauchy-Schwarz another time?
Here?
No, in the top one.
Okay, here?
The one below?
This?
Yes.
Okay.
So just directly
Well,
by Cauchy-Schwarz, we have that sigma i's are just zeros or ones, right?
they're plus ones or minus ones.
So
They're scalars,
so
yeah.
the norm is m.
So I could just do it right there.
Yeah.
Yeah.
You use order 1, right?
Yeah. What's that?
You wouldn't see the randomness.
Okay, you lose.
We'd have order m over m, order 1.
So you get a better bound, is that what you're
Yeah,
saying?
of course. It's like a random walk in n steps that lose root m.
Okay.
Yeah.
The norm of sigma is square root of m as a vector, no?
Well,
Plus 1 plus 1 plus 1 square root. Square root of m.
well, I can't think on my feet, so let's just check that. There's one other remark I wanted. We come back to that. The other remark I wanted to make, though, without redoing it, is that if we go to the kernel case, and I know I didn't explain it, so I'm kind of leaving in the dark a little bit, but the kernel version of this, okay, instead of w dot x, it's inner product of w with phi of x is your function, which is just the same. Okay? And everywhere you're going to see xi dot xj becomes phi of xi dot phi of xj. And so the only difference that you're going to see is that when you pull out, when you do Cauchy-Schwarz, it's a little bit different. So actually, maybe this calculation, you see it. You take an expectation over sigma of a sum sigma I phi of xi h Okay, so what pops out is the norm of the functions. So you need the f and the h norm to be less than or equal to lambda, rather than just rather than w less than or equal to lambda. So it's a very similar calculation, except now we have an inner product space, and you replace, what I was saying before, you replace this with this. Okay, but the calculation otherwise is the same. Okay, that's that. Let me look at my schedule. Okay.
Is Rademacher complexity always independent of the dimension?
No. No, it's whatever it is. In this example, it's independent of dimension. So the generalization bounds we want are independent of dimension.
So you didn't write the dimension, it doesn't matter, but it could turn out.
Yeah, if it was, then it would just be a slightly less useful bound, but it's still the Rademacher complexity.
Okay, but what I got earlier is that it's sort of useless if it depends on the dimension. Or
It's less useful.
less useful.
So V.
All Lipschitz functions or something. So it would have the cursive dimensionality.
Yeah.
So are those bounds on the norm of the parameter and the features kind of hiding the dimension implicitly?
In the second one or the first one? Well, the first one, there's nothing hiding. It's okay. Look, there's one thing I guess confuses everyone, which is two separate questions. Can I fit with the small norm of W, right? Can I fit with this constraint? And this says nothing about that. So if you have data that's like random, then, and you have good Rademacher complexity, then you probably won't be able to fit your data without overstepping this bound.
So my question is, if let's say your features are IID, and you increase the dimension, then we expect the norm to increase proportional to the dimension, right? So
I don't know.
I'm not implicitly finding the dimension.
I mean, I don't know. I don't know. It's not curing everything. It's just it's a sufficient condition to get the bounds you want. Doesn't mean you're going to learn. Okay, so let me back up once this pops out. So this was, the most, I guess, to me, it seems to be the basic bound you want to get. There's more bounds. You can generalize other things. I'm not an expert in this, so I looked at the papers on local Rademacher complexity. You can get slightly better learning bounds. There's more literature on this. I was just trying to get a feel for these bounds. So we got that. But let's go back. Why am I personally interested in this? And now the rest of this talk is completely just my personal thoughts. So I looked at this because I wanted to see can we do some regularization on deep neural networks. Okay, the stuff that's very architecture specific I'm less interested in, but I would hope that if we could just deal with nonlinear functions, so non-parametrically, separate whether you can fit any function. Let's assume our neural networks are so good you could fit anything. Now let's try to regularize them so that they generalize. Okay? So what's the difference? Well, they're nonlinear models now. That's fine. We're not going to use nonlinearity, the linearity like we did in that calculation. So that's the hypothesis. Add regularization. Well, if you look up, there is regularization in deep learning. It's not exactly a mathematically rigorous version of it. Okay? The naive stuff, they call it weight decay, and they just add W squared to the loss. A, it doesn't do anything. You don't need to do it. B, it's not really the right regularization. It's not, because the neural network, unless it's one layer, is not an SVM. Okay? So you're supposed to be regularizing the function, not the W's. But there's a whole bunch of other things they do that they call regularization, and the early literature on deep neural networks had regularization. Those guys did know Taylor expansions. So in '92, they did Tikhonov gradient regularization. Okay? They also added random noise and showed that it's kind of equivalent to a type of Gaussian regularization by a Taylor series expansion. They do, I consider data augmentation to be a form of regularization, soft, not rigorous regularization. That's where you just wiggle your images a bit so that your network learns to deal with slightly different versions, and then it generalizes better. Dropout was regularization on the weights. Instead of training for a fixed weight, go wiggle the weights and see if that gives better generalization. Cutout is really cool. Cutout is, instead of showing the true image every time, you just average out or cut out a square, a random square in the image and train on that. Heuristically, it's supposed to say, oh, I won't be attached to one particular feature. I'll have to learn multiple features of the image. More recently, mix-up is taking little convex combinations of your data and convex combination of the labels and training on that. So to my mind, all this is sort of taking your original sample and growing it a little bit, but in a way that you're preserving the correct labels. So you're augmenting your sample with the correct labels. And recently, Gaussian noise averaging the model and then averaging the prediction. So it's like convolving your model with a Gaussian, and that one you can actually prove the convolved things gives you bounds on the gradient of the model, which you didn't have before, or if you had them, they were vacuous. Okay, so I go into this a little bit. You could take anything, like data augmentation, any transformation, you could just add and subtract it and say, it's my original loss plus a regularizer, which is this difference of the losses of the perturbed image and the other one. Is that useful? Is this a regularizer in any mathematical sense? Maybe not, because this term doesn't even have to be positive, right? But we can expand this and see under some circumstances it may be. So if you did an expansion of this, maybe it's like a gradient term. So this is the old calculation I sort of redid from this decades-old paper that says adding random noise to your images is equivalent to regularizing. They sort of implied it was just this. There's some extra terms, so there's a Laplacian term and a Laplacian squared term. So just from Taylor series, you see that something like this is what you get when you add noise up to, and there's a little proof of it here, but it's Taylor series stuff. What does that mean? It doesn't, we're not doing anything with it. We're not saying that when you regularize with this term, you have generalization. It's just to sort of see if there's a connection between these hacks and mathematical regularization.
Does that lead you to, maybe not, but give you maybe some kind of estimate of a bound on what you could prove about,
Yeah.
Now you get, like you said earlier, you get your one image and you've got your trained network.
Yeah.
And you want to be able to say with confidence that it's something that will be classified correctly if it's within.
Exactly. That's exactly what we're hoping for. We're hoping that if you have this, so yes, if you have bounds on the gradient, so the basic estimate is this. Your neural network, here it is, you think you're doing great, but it can just jump there and you don't control this. If you just train to minimize the loss, here's my image, it's supposed to be flat in this zone, and now I have this huge jump. Okay? Now the average network gives you a global bound on the gradient. It says that even though whatever my value is here, it can't change with a slope bigger than this slope. Okay? And that tells you that now if I know my loss here is very small, and I know I have to get up to this loss in order to misclassify, I've immediately got a bound on the distance where my classification is constant. So that's exactly what you want. So far, the only way to get a global estimate of this slope is through averaging. But it may be that these other things certainly seem to help. And in fact, when we implemented Tikhonov regularization, again with Chris, and we just empirically measured the gradients that we saw, it made a huge difference. Like you got way smaller gradients at the images and even nearby. So, so that seemed to be a fruitful direction to go. And this is just to say that people were kind of already doing that, but then they moved away from it. So there it is, adversarial training. The regularizer for adversarial training is the gradient of the loss in the direction of the perturbation, and the perturbation happens to be the gradient, like this. And so that's the Tikhonov regularization that we implemented, which helped. Problem is, adversarial training, basically everything people do helps your adversarial robustness by a certain amount. And they're all roughly comparable. Nobody's made an order of magnitude better adversarial robustness. They went from here to here, and then they got stuck, and we'd like to be over here. So we love this Tikhonov regularization, but adversarial training is basically equivalent, and it's equivalent performance, and by Taylor series expansion, it's almost the same thing. So this paper got rejected many, many times. Okay. So I think I'm just repeating myself here. Yeah, okay. All right, so that finishes talk 1, which was designed to be longer. Now I have a shorter talk, basically on SGD. Okay, it's so tiny. So it's going to be a similar format where I'm going to show some slides to give a feel for things, and then there'll be maybe a 10 or 15 minute Blackboard proof, a little bit shorter than the other one. And then I've got some more slides if we have time. So this is repeating that stuff. Okay, so we train with this convex law. So, I got into this when I was visiting UCLA 3 years ago, and we thought, wow, where can we go with this? The most mathematical aspect of deep learning, where it's clearly the math is going to help, is the training, because you're doing optimization. And you're doing optimization with stochastic gradient descent. It took a while, especially talking to my colleagues, who we've all got, there's tons of knowledge of optimization, and yet the practices in deep learning are so different. I grew up on Newton's methods, second order methods. Gradient methods were too slow, because if you have a Hessian, you can solve a linear system and get super fast convergence. Now, in machine learning, everyone uses gradient methods because the size of the data is too big to build a Hessian and solve that linear system. Then they stopped using gradient methods and they used stochastic gradient methods because you can't even compute a full gradient of your loss. Okay, so that's basically the idea. SGD is slow, but if you read this review paper in SIAM by Leon Botu, he makes the point that there was kind of a revolution in optimization for machine learning where they realized, optimization is always about trade-offs between different costs. You can revisit your data many, many times, and that's what SGD is doing. An epoch is little steps covering some of the data. And it's still faster than trying to solve one big hard problem with more memory than you can afford. So SGD trades off the fact that you have too much data by visiting it many times and making incremental progress that's slower than if you just took gradient steps. Okay, so where's the math? This is sort of a cartoon of SGD. So this is in 2D. Imagine this is all my data. But imagine each of these things is like, each picture here is the size of my hard drive or whatever. Okay? I'm trying to minimize, I call this the one mean clustering problem. The sum of the distances to all the points. Find the average. Okay? This is a hard computation. If you asked me for the average of all the images on Facebook, how the heck would you compute that, right? It's distributed. So what would you do? You'd take as many images as you could put in your computer, average them, and then grab some more and keep going until you'd averaged everything. Okay, and so that's the picture here. Now we've got a mini batch. It's not just one. That would be, the original Monroe-Robbins SGD was just minimize one at a time. So we've got a mini batch here. We compute the gradient of the loss of the mini batch, which in this case is just pointing towards the average. And you iterate. And the point is that unlike gradient descent, where you can take steps that are always the same size, like 1 over the Lipschitz constant, the quality of the gradient that you get is worse the closer you get to the minimum. Okay, so out here, if I'm averaging and I'm sitting here, almost all my points are pointing in a good direction towards the average. And that's why you see these arrows. So I could take a big step. Maybe I can overshoot a little bit, but I'm going in the right direction. I'm not worried about overshooting because we take small steps in the end. But now when I'm sitting right here, if I take a mini batch and I'm unlucky, maybe half of them are on this side and half of them are in this direction. And I don't get a very good vector. Yeah?
How do you go from step 1 to step 2? So you pick your
What?
first batch and you compute.
Oh, just randomly.
Okay.
So,
How do you throw the other guys in there?
okay, in practice, it just depends on how your memory calls work. But one thing you might do is divide your data set into 100 different batches and just visit each of them. Right? Or you might just randomly, with repetition or without repetition, resample from your data. But in practice, it would depend on the actual geometry of your distributed data and what you can get. I'm talking about batch SGD. There's also online SGD, which is where your images are they're just coming in, right? They're just on the internet. You don't get to see them again. But that's not as important of an algorithm for what we're talking about. Okay, so back to this picture. When you're here, your gradient's not as likely to be good, but still, on average, you expect that it's pointing in the right direction. So what you do, you either take tiny steps, one at a time, or you could take more gradients, right? I could measure my gradient 10 times, add those up, and then take one step. Well, it's mathematically kind of the same, but in practice, it's easier to take 10 little steps and just keep going. Okay, so that's the SGD algorithm. Here is what we're going to prove. Okay. So you've got this. So we're going to basically model the error. I don't think it's written down here. The mini-batch gradient is the true gradient plus an error. And the error is mean 0 and let's say variance sigma squared. That's a modeling assumption, which is not exactly correct, because further away the variance might actually be a little bigger. But it's good enough for what we're doing here. So this is SGD. Now you have to choose the H. And the key thing is what you want is a 1 over k scaling for your H. Okay, so the 10th step is scaled like 1 over 10, and the 1000th step is much smaller, 1 over 1000. All this is kind of like telling you where to start k at. If this number is 12, you start k at 12. Now this is the strong convexity parameter. We're assuming it's a convex, mu-convex function. I'll write that down, what that means in a second. This is just a constant in front of the k. And for flatter functions, it's going to be a smaller number. Okay, so we might take bigger steps. That sort of makes sense. This is really flat, you can go further. Okay, now if you use this particular sequence, then what we're going to prove is, we're going to prove that you get the rate. This is the 1 over k rate with a certain constant that we'll write down. So that's the idea. Now if you look in the literature of SGD proofs, there's a whole bunch of different proofs. You don't have to do it the way I'm doing it. What I'm doing is a Lyapunov technique. Okay, I'm going to take an energy, which is just, the energy is the distance squared to the minimizer. And I'm going to show that it decreases. That's what this is saying. In expectation, going from the previous step to the new step decreases the energy. It's not necessarily the only proof. There's proofs for averaged SGD. But what I found is looking at the big picture, this Lyapunov approach is sort of a unified approach that you can apply to Nesterov's method, the non-stochastic version, and a lot of other things. So it seems like a good general approach. Okay, here we go. Okay, so I first saw the definition of convexity in Craig Evans' textbook. Who else saw it there? It's like we're fans. But he really sold out in the 90s. He was a rock star. No, I'm just kidding. I'm just kidding. I'm saying I'm a fan of Craig Evans. No, I'm kidding. I'm saying like I was an early fan. His later stuff, it's not the same. Once he got really famous. But no, I'm just kidding. It's a joke. I love Craig Evans and I love his stuff. And I saw this picture. There's not a lot of plots in the book, but the one you see, right, is this. The convex function f of x, right? You have a point that you're going to sample. Let's call it x. And you're going to do an affine approximation. So supporting hyperplane, he calls it. Right? The supporting hyperplane is, I'll just write it as a of y, is the function right? And convexity means, we say that f is convex, so notation, let's call x star, let's just assume it's unique, the minimizer. So it's there. And the definition of convexity is that this affine function y is below the graph of f of y. Okay, let me call it ax to tell you where it's centered, for all y, and also for all x. That's f is convex is equivalent to that. It's also equivalent to the usual thing where you take a secant and it's below when you average, but that's fine. That's what the definition we're going to use in optimization. And really, so let's look at this difference. If you can push it even further and say that there's a little quadratic gap there, then that's the definition for all x and for all y of mu strongly convex. Okay? And now, you might have a function that has a corner in it, in which case it can really jump faster than quadratically above its supporting hyperplane. That could happen, but if that doesn't happen, if there's always a quadratic above that you can fit above. So in other words, if this thing is always less than or equal to some L, x minus y squared, 2, then we say it's L smooth. Okay, so this inequality is mu strongly convex, that one's L smooth, and it's controlling how much you grow above or below the supporting hyperplane. Okay, and an example of that, this is equivalent to, both these things are basically saying that if the Hessian is the second derivative, that its eigenvalues are between mu and L. Yeah? What's that?
I mean F, I guess.
Oh yeah, F, sorry, yeah, F. Okay. So that's all we're really going to use. Oh, we also call, in the case that you have these constants, CF L over mu is the condition number. So we care about badly conditioned problems. When you do classification, you lose strong convexity. So you're dealing with the convex but not strongly convex case. When you regularize, like that little bit of margin, the parameter lambda is how much strong convexity you're adding. So you add more, it's better to optimize, but at some point you're asking too much. So we really care about the case where this thing is large or going to infinity. Okay? So let's define SGD. So we got the algorithm for SGD is this. So we're going to use that. I'm going to go ahead and define my learning rate. So the scheduled learning rate is to set and I'm just saying that K naught, there's a lot of constants flying around. Alpha S is going to appear in the rate, that's why I'm defining it. Okay, and now Q of X that's just the distance squared over 2 to the optimum point. And QK is just shorthand for Q of xk. And M, the M that you see here, it's a bit weird to see it, but it'll be the maximum over all k in our algorithm of so it's the biggest gradient you'll ever see. It seems kind of cheating to define it that way because we haven't seen the gradients yet, but it's okay. We can get around that. anyways, what usually happens is you start inside a certain domain, and you have a bound for the gradient in that whole domain. And unless you screw up, you're going to only stay inside the domain. So that could be your M. Okay, so what's the theorem? Oh, I don't have the theorem yet. I have a lemma. Okay, so actually this is important. So if you look at these proofs, whether you're doing SGD or whether you're doing Nesterovs, there's sort of one lemma that lets you approximate taking one step of the algorithm. You take one step of the algorithm, you get a term that's decreasing your Lyapunov function, and you might have some remainder. Okay, that's the basic lemma. And then when you iterate that, in our case, we're just going to sum the remainders to get the rate. So this is basically a two-step proof. Okay, so the basic lemma we're going to use, in both cases, we're going to use the convexity. So the lemma is this. So with all these definitions, how much does Q change given xk? And I'm going to bound it like this. Okay, so I forgot a couple other little things. So I'll write gk, it's just a shorthand for the gradient at xk. And remember that grad mini batch of f of x is equal to grad f at x plus some random thing. Okay, that could be random, but the point is that the expectation of E is 0, and the variance of E is sigma squared. This will be applied at xk, and then there'll be an E, which is a function. Could be a function of x, but also of randomness.
Does that depend on the choice of the sequence that you generate?
No. So there's two cases. There's the stochastic approximation case, where this is just a random vector. It could be like a random draw of noise. That's like the more physical or engineering SGD case. Case 2, the mini batch case, you're actually taking your mini batch of size 100, and you're looking at how bad an approximation that is to the true gradient. And so we're making this assumption. There's some error. All we're assuming is it's mean 0, and we're bounding the variance.
But can you design it, though? Is it hard
Oh,
to
you mean,
do, or
could
like
you design?
Running the scheme,
Yeah, I mean, I see what you're saying. Sorry, I misunderstood the question. Some people think that you could pick, maybe it's better to adaptively choose which points you're sampling or something like that. That's a possibility. I don't think it's
so
super.
This is done by convenience in practice.
This is just a modeling assumption for the proof. In practice, if you get into what people actually do, there's like acronyms full of different algorithms. There's SAGA, there's ATOM, not named after me. Okay, there's a million of them, and they all involve different types of hacks, and they are particular to the application. So if it's online SGD, you have your own version. There's variance reduction, which doesn't work in our setting, but where you try and reduce the variance by taking a full gradient and then perturbing it. So there's a million hacks that people do. And some of these algorithms that work well don't have a proof. There's things where you do running averages of everything as you go, and they've shown that the algorithm diverges, in certain cases, but it works great in their stuff. But so we're being very just abstract mathematical. Okay, so this is the lemma we're going to show. So actually, this term, we could kind of just absorb it into there right away. We don't really need it. But we're showing this 1 minus mu hk qk. So we've decreased q by this factor. But there's a price we pay, because it's stochastic, and the price we pay is, luckily, hk squared times this positive term. Okay, so once we've proven this, it's going to be just balancing out making h smaller so that we can sum these things up. The proof of this is pretty short. So let's subtract the qk's. And by algebra, so this is just an identity. It's, if you just multiply it all out, it's a quadratic function, so you'll see that this is true. But now we're going to use SGD. SGD is telling me something about the difference between xk plus 1 minus xk. I've got the h and I've got the gradient. And I'll just rewrite that as okay? So I just plug in the h and the g there. So it's minus hk O. So it's that. Okay, so that's pretty simple. That's equality. Now the inequality is where we use strong convexity. Actually, I don't even think we use L smoothness here. You just need it to make sure your very first h is not too big. But then after that, you're fine. So when we do strong convexity, this is my q. I'm going to take y to be x star. And so there's my quadratic function there with a factor of mu. And so when I apply it, now the last thing I do, which I haven't done yet, is to take expectations. Yeah? No. Take expectations. Take expectations will kill that one term. So there's the linear term in E that goes away. And this is going to become my gk squared and my sigma squared. Okay, so that's going to be there. This is the term we have when we put the qk on the other side. And we just do strong convexity again to absorb this, to compare it to the quadratic. Okay, so that's very quickly the basic lemma. Okay, now we're just Now we're just going to use this to prove the theorem. Should I use this board or go back to that one? Maybe that one's a little, because it's a little bit blocked. Should we do it? People seem tired. I could just tell you what happens. It's beautiful. It's beautiful. What do? You plug in these complicated definitions with the alphas. Okay? You plug it into here. You start adding things. And you get a lovely cancellation between, you're looking for, how am I going to get a 1 over k rate from all this? Well, I'll just tell you, this guy translates into something that looks like 1 minus 2 over k hat, where the k hat is my k plus 1 over q naught alpha. Okay, and the alpha term has the sigma squared plus the m squared in there. So you fool around a little bit, and you end up getting a -1 that pops out, and that's the rate. You guys look too tired to do the details of the proof. Okay? It'll be on the PDF. The proof is right here. All right, let me go back to the blackboard. So I wanted to show you this to show you that these SGD proofs are not so hard. Okay? You do get this 1 over k rate. the constants sort of matter, right? You see the convexity, you see the noise, you see the gradient bound.
Is it false without that box? Is there any
No, there's a million things you can do. So if you read the review by Botu, he has a version of the basic lemma, okay, where he completely relaxes this simplifying assumption, and all he asks for is that the condition grad f unibatch, all you really need is that the dot product of that with the true gradient is that you can control that they line up sufficiently. There's a right-hand side that you can control, that this is bounded below. So you don't want this to be 0 or negative. So you want to just control this by something of the form. We have...
And the same HK is chosen, similar...
Right, that's a good question. Yeah, the learning rate for these proofs is always 1 over k for the strongly convex case. Actually, let me go to the slides now because I'll go over that. In the convex case, the rate is 1 over square root of k, and the learning rate is 1 over square root of k. Okay, so SGD. So 1 over k rate, 1 over k time step. Convex case is slightly different. But now let's talk about acceleration. So in practice, everybody uses Nesterov's acceleration to kind of speed things up a little bit. So I want to give you a bit of a feel for that. So there's this beautiful web page where you can see illustrated momentum, the momentum algorithm. So this is, I haven't told you what the algorithm is yet, but I'll show you in a second. Basically, instead of doing a really slow gradient descent on this function, here we go. This is gradient descent. You zigzag, and then you take really tiny steps near the minimum, and you don't make it here. If you replace that simple algorithm, there's no stochastic anymore. Okay, this is full gradients. With this other algorithm, then you oscillate more, but if you tune it just right, you go way closer, faster convergence rate to the solution. And it's basically for free, because you've got one gradient there, and here you've got one gradient, but all you're doing is some kind of extrapolation from your previous values to your next value that you then plug in to the gradient. Okay, so it's called Nesterov's accelerated gradient descent. There's more than one of them. Actually, there's two different versions. One is for the strongly convex case, which I didn't write down, and this is the one I wrote down for the convex case. The difference is for gradient descent in the convex case, you get an exponentially fast rate that depends on the condition number. So it's something like the rate in your exponential is something like this. So really big condition number, this thing is not contracting very fast. And for Nesterov, it's more like something like this, which is a lot faster. You've taken your million and changed it to 1,000. Okay, that's what they prove about the rates. Okay. So yeah, there it is. I wrote it down. In the convex case, gradient descent is only 1 over k. That's super slow. And acceleration means you accelerate it to 1 over k squared. That makes a big difference. After 1,000 steps, you're talking about 1 over a million versus 1 over 1,000. Now, what's weird about this algorithm is Nesterov in his book proves it, but he proves it using a method of estimation sequences, which gives you no intuition and hasn't been used in any other way. He also proves lower bounds that you can't do better. In other words, he shows that there exist functions and initial data points where if you apply any algorithm that just uses gradient information, it can't converge at a faster rate. And the example he uses to prove this is essentially the 1D discretization of the Laplacian, the 1D Laplacian on a grid, which we all know is really slow if you do forward Euler. So that's interesting. But basically, there's a lot of people wanted to interpret this in some way with the goal of building faster algorithms. Okay? And so Sue Boyd and Candes showed that this algorithm here you can interpret as the discretization of an ODE. And they proved that the ODE decreases a Lyapunov function like 1 over t squared in time, whereas gradient descent just decreases it like 1 over t. Then they showed that when you discretize it, you get, with a time step, a constant time step, you get the rates that we saw. So that was quite exciting. And then Michael Jordan at Berkeley and a bunch of his people in his group did a bunch of papers trying to do stuff with this algorithm in continuous time. The problem is you go from, so the best proof of Nesterov's rate is actually not Nesterov's proof, but there's a Lyapunov function rate in the, for the subgradient case that's 2 pages long. But these proofs started being like 60 pages long. I don't know if they use computer algebra or what. They're just like formulas after formulas with no words. And so it doesn't really give any insight, and it's not clear that they actually built any new algorithms. So you sort of wonder, if there's a promise here, what would the promise be? Anyways, this is Sue Boyd's ODE. Look, it's friction, acceleration, and force. Okay, and you can write this as a first-order system like so. If you just solve for one of the variables and pop it back in, you get the second-order system. Stan's falling asleep. Don't worry, we're going somewhere with this.
This doesn't work for SGD. This is gradient descent with only.
We're talking about gradient descent, but what I'm saying is maybe the direction we should look in is if you can do Nesterov's accelerated version for SGD. That would be great.
Yeah.
Okay, so first off, we said, let's do it. This is me with Maxime Laborde, my postdoc. We added one term to the ODE that Sue and Boyd had. This wasn't there, but it's a really small term because it's 1 over square root of L. When you plug it in to get a second order ODE, you get Sue Boyd's ODE and some new stuff. The cool thing about the new stuff, well, here's some friction that decreases in time. You actually get a Hessian term popping out. So this thing is interpolating between this ODE and the ODE for Newton's method. And actually you can prove that this thing decreases the same Lyapunov function faster than the Sue Boyd one. So this helps. In addition, you discretize this, you get Nesterov's method. So a bunch of ODEs were studied in continuous time by Alvarez and Atouche. Actually, this one that we came up with turns out is a special case of a whole family, one parameter family of ODEs studied by this Shi and al. In 2018. But that's too much. If you just use this one, all the proofs get shorter and cleaner for Nesterov. So that's why I'm doing this Lyapunov function approach. If you want to understand Nesterov, you can see a nice clean proof using this ODE that's short. Okay, and so here it is. So I'm going to discretize this ODE, this guy up here, forward Euler in time. Okay, I'm going to allow for a variable time step, but later that's going to be just constant, 1 over square root of k. And the thing that everybody does, you don't evaluate the gradients at x. The way to get Nesterov is to evaluate them at y, where y is an average of your 2 variables. It's a convex combination that's very close to x with this factor. Okay, so you evaluate your gradients there. It's just forward Euler, but you evaluate it at a point, which is a convex combination of your 2 variables. And when you stick this in, you get Nesterov's method. Fine. Okay, so what? This is sort of what I'm saying. It's nice. I like it because it's cleaner math. But at the end of the day, what we want is an algorithm. And the algorithms we care about, we know they've proved you can't do better for gradient descent. For SGD, though, maybe there's an accelerated version. And people have tried different versions just heuristically of acceleration with SGD. And there's no lower bound. Okay, for SGD, there's a lower bound on the rate in terms of the function of k. It's 1 over k. You can't do better than 1 over k, but there's no lower bound on the rate constant. So there's a possibility that an accelerated algorithm could give you a better rate constant and maybe work better in practice. Okay, so I'm just redoing this. This is just rewriting it again. Okay. I feel like I'm going in circles here. Let's stick in stochastic gradients just like we did before. Let's stick it into this version of our ODE for Nesterov. Okay, so what happens? Before we do that, let's just do the heuristic. This is what accelerated SGD does. This is your perfectly tuned SGD. Okay, it goes down like 1 over k. That's what the proof says. But in the first, 25 steps, Nesterov, it's like the noise and the gradients don't matter. It goes down faster. Then right away it gets to this threshold because you're using a constant time step, where now you might as well just stop, because now it's just going to oscillate, and eventually SGD catches up. But in practice, what you do is when you get to this point where things are, on average constant, you shrink your time step again, and you hope that you're going to get another dip and keep going with Nesterov. So when you train neural networks, you do this about 4 or 5 times. Nesterov, accelerated SGD with a constant time step, go for a while, and then shrink it down again.
There's an alternative method where you restart.
Yeah, restarting is cool too, yeah.
That's different.
Restarting has to do with if you've, I don't know if I have this picture really early on. If you mistune Nesterov, so this is good Nesterov, perfectly tuned, but you've got to start worrying about tuning now. And if you, I don't have the picture. If you have the wrong tuning, let's say you started with k too small. You were here, k is supposed to be 1,000, but you start with k equals 1. Then you don't have enough damping, and you start just oscillating like crazy. Now what you can do if you haven't tuned it right is notice this oscillation, notice that you're on the wrong level sets, and restart back to k equals 0 or whatever you want. So that's a way to deal with the tuning, but it doesn't change the ultimate rate. It's never better than if you'd perfectly tuned. Okay, now this is supposed to be a tutorial, but now I'm going to talk a little bit about my own work for a short amount of time. So we took this thing. This is the ODE, where if you stuck in a constant learning rate of 1 over square root of k, you get Nesterov. And now we did the Lyapunov function analysis to get a convergence rate, similar to what I showed you on the board. And what we found is, so this is for the convex case. Normally the convex case, you have a square root scaling. The optimal scaling is a power of 3/4, which is faster. And so you add up the times. That's your algorithm. It's a variable learning rate, stochastic gradient with this weird exponent. And here's what happens. And this is robust. So this is SGD on a convex problem with a big condition number. If you tried to tune SGD, you can't do much better. So this is just playing with the tuning. And these are 2 versions of our algorithm where you didn't tune it too hard. This is where you just threw in a guess, and here's where you tuned it a little bit. And so it's,
So tuning,
there's parameters in the algorithm. It's your initial h and the constant in front. So you could start with k equals 1 or k equals 100. You could multiply it by 1 or by 10. So c is what you're multiplying by. We're starting at k equals 1. So we just wiggled the c and we got it faster. The important thing is this is easy to tune and is faster.
just keep tuning the shape.
No, I just tried 2 c's and then I saw that you didn't get much better. Everybody tunes their algorithms. So I wanted to show that this is the best tuned SGD and this is my algorithm and it's faster. Same thing with a different example. So same idea. If the condition number is 1, it doesn't do that much better. But when the condition number is big, it does a lot better. So you do better with worse condition, relatively better when you have a worse condition number. So that's cool, but I haven't shown you the proof. So we actually prove the optimal scaling rate for SGD, but with a better rate constant. So here's a table. So we have 2 versions of the algorithm, just like Nesterov. There's the strongly convex version, and there's a convex version. In the convex case, this is the usual learning rate. This is our learning rate. And the important thing is, in front of the rate constant, so there's a log k over k, you see this g squared. This was the bound on the gradient plus sigma squared. So this has the biggest gradient you see of your function, which could be 100. Sigma squared could be 0.1. Ours gets rid of it replaces this with just sigma squared. So it's a better rate constant that doesn't see the size of the gradients, just the amplitude of the noise, and you see the same pattern here. These guys all have the g squared. This one even has the condition number, and we got the sigma squared. So we prove a better rate in terms of the constant. And we do this with the Lyapunov analysis. And so there's the proof, basically. And so let me just briefly do the Lyapunov analysis. So the way we did the algorithm was to do the following. We know Nesterov converges fast. We did a proof for SGD like I just showed you. You take the same Lyapunov function for Nesterov, you discretize it, and then you want to show that when you do the stochastic version, you can get a rate. But it's kind of a pain to do that because Nesterov's algorithm is a bit complicated. And so instead of doing it for the specific OD and Lyapunov function, we did an abstract analysis. We said if you have a general Lyapunov function and a general ODE, what properties do you need? It decreases the rate. And then we proved, like the proof I did on the board, that it decreases and you sum things up to get a rate. And then we applied it to the Nesterov algorithm. So there it is. You have the abstract stuff. The abstract thing works in continuous time, full gradients with constant time steps, and stochastic gradients with decreasing time steps. Okay, so that's the idea of this. I think the benefits of this approach is you can cover SGD, accelerated SGD, gradient descent, accelerated gradient descent with this one proof technique, which is pretty elementary. So I'll stop there.